Good morning, everyone. Welcome to the University of Bergen in Norway and the joint lecture at the course on concurrent programming and the seminar at Bergen Language Design Laboratory. Today I'm very happy to introduce Vitaly Bragilevsky from JetBrains and St. Petersburg State University. Vitaly is very well known in the Haskell community. He has a lot of teaching experience of functional programming. He is the author of the book which is called Haskell in Depth, which will be published soon by Manning. And Vitaly is also one of the 11 members of the Glasgow Haskell Compiler Steering Committee. So we are very happy to have Vitaly talking to us today. I would also like to thank the external participants that have joined us today from several countries. So, without further ado, I'm very happy to give the floor to Vitaly.
Okay, thank you, Mikhail. So let me share my screen here. All right, I hope you can see my slide now. Okay,
yes,
great.
Yes.
Thank you. I'm not sure that I will be able to see chat at the time of the lecture. So please, whenever there are questions, please ask them out loud. That will be more convenient for me. Okay.
Yeah.
But,
so if there are some questions in chat, I will then just read them out loud for you.
Yeah. Thank you. All right. So this is a talk about concurrency in Haskell, and of course I don't expect that you are a Haskell professional, and well, I don't expect, in fact, that you know Haskell very well. Maybe I will give some short overview in the very beginning. But my main goal with this lecture is to tell you about one, as I think, very good way to implement concurrency in programming languages. It's funny that concurrency is something which can be done very differently. And every programming language takes its own way to implement concurrency and to give concurrency programming to the users. So we'll see how this can be done in Haskell. And as far as I know, during this course, you will see other examples from other programming languages as well. So this is very important to see different sides of concurrent programming in different programming languages. I will start with several facts about me. I work at JetBrains, and I also work at St. Petersburg University at the Department of Mathematics and Computer Science. And there I'm responsible for study program in programming, in modern programming. I'm also a member of GHC Steering Committee, and at that committee, we are doing one simple thing. We are looking at the proposals to extend Haskell compiler, the most well-known Haskell compiler, Glasgow Haskell compiler, and then decide whether this proposal should be implemented in GRC or maybe it's not good enough, it's not appropriate for GHC. So that's the goal of the committee. So we're working with the most actual features in Haskell compiler. And I'm also the author of the book Haskell in Depth, and the last chapter of that book, and I'm working on that last chapter, is devoted precisely to concurrent programming. So this lecture for me, preparation for this lecture was like writing the last chapter of that book. It is not published yet, but hopefully it will be soon. If you are interested, here I have slides. These slides are already published. You can find them on this web page. So if it's more convenient to you to follow slides by yourself, then feel free to download them and to follow my lecture. So it's just precisely this version of the slides. All right. I'll start with a short overview. So of course, it's not a tutorial on Haskell programming. Instead, I would like to talk about several features which are the most important features for Haskell and for concurrent programming. So this is a very first example of a Haskell function. It is very popular. It is called quicksort, although it is not quick at all, and there are a lot of problems with this function. But anyway, you can see this example very often. So let's look at different parts of this definition, just to get a glimpse of what is Haskell programming. So in Haskell, we write functions, and functions usually start with type signatures. The first line here we have a type signature. And in this type signature, we say that this function takes a list of integers, and it returns a list of integers. Then we define this function using function clauses. So here we have just one example of a clause. And we write those clauses using pattern matching. So for example, in this line, we say, well, if this list, the given list is empty, then we return empty list. Second clause is if we have a list with the first element and with some tail, then we can compute the result using this expression. Almost everything in Haskell are expressions. So we compute something, even if we do some input output or whatever, we are computing things. So we express that using expressions. Of course, we can have some local definitions, like here, lower and upper, they are local definitions. We define them not as separate top-level functions, but as local definitions. They are also expressions, of course. Here we have an expression. And in those expressions, we very often use higher-order functions, functions which take other functions as arguments. For example, here, function filter takes a predicate function, a function which returns bool value. So here, this is a very basic example, but we have to be able to read type signatures to functions. And then we need this idea of everything is an expression. So we can program using expressions. All right. Sometimes our types are a little bit more hard to read. For example, here we have a function, lm, which checks whether an element is a part of some container, a container or something which we call foldable. List is foldable, sets are foldable, and many other containers, data containers, they are also foldable. So we call these foldable type class. Another type class is eq. This is a type class which allows us to compare whether two values of some type are equal or not. So we take an element of type A, we take a container foldable with elements of type A, and then we answer true or false, whether this element is an element of a container or not. So when we read this type signature, we see the first section before the right double arrow. This is these are type classes or constraints. They constrained our type A and T. Then we have types of arguments, and type of result. The last one, the type after the last single arrow is a type of result. So in this function, we have two arguments and one result. And whenever we see such signature, we can understand, well, these are arguments, and in the end, we have a result. And we also here, we have an example of polymorphic function, because we write function lm once, but we can use it for values of many types, like list of integers or a set of strings or whatever. So this is what we usually call polymorphism in programming. All right, these functions, quicksort and lm, they are pure. When we say pure in Haskell, we mean that there are no side effects. Like these functions, they just compute the result. Whenever we see list of int or bool in the argument, in the type of result, we understand that these functions are pure, because by default, every function is pure. We cannot do input output inside those functions. We cannot run concurrent threads. We cannot do anything besides computing bool using arguments that we have. And the result is determined by arguments in a single possible way. So this is purity. But of course, whenever we do input output, or if we want to do concurrent programming, we need something different. We have to work differently. And in Haskell, this is a very important feature, we can say that specifically in a type signature. For example, here we have a function getLine, which inputs a string, and we can see that this is a function with effects from the fact that the type of result is IO string. This IO here says that to get this string, we have to do some input output. So in this type, we can show specifically what we're going to do to get this result. So it's not just string, it's IO string. For example, here in this function, we input some string and then we print another string. We input name and then say hello, this name that was entered by the user. So whenever we have effects, we need to sequence operations. So we have to say this is the first operation, this is the second operation, and so on and so forth. And for such sequencing, we're using do notation. So it's a little bit different from what we've seen in quick sort function, for example. So we have a sequence of operations, and we do that using do notation. And the important thing about Haskell is that it's not only a feature of the IO, it can be used for other things as well. So IO here just determines some set of operations that we are allowed to do here. We call these functions IO actions. So action, like we do input, we do output, and in fact, in IO, we can do everything. But know this idea. In Haskell, we have a possibility to determine set of operations. And we can determine it in different ways. And in fact, this is just an example of a general mechanism for implementing some sorts of sequential computations. And we'll see that this feature is extremely important for Haskell and for concurrency in Haskell. Because when doing concurrency, we'll see that it will be important for us to limit some set of operations, to say that, well, this is allowed and this is not allowed. And this is a feature which absent from many other programming languages. And for concurrent programming, this feature is very important. So we'll see one feature of Haskell, which works in Haskell just greatly, but it doesn't work in other programming languages because they don't have this feature, because they are unable to limit set of allowed operations using this general mechanism. Okay, so but it's okay to understand only one thing. Like when we use this IO in the type, we say, well, in this function, we are limited with some set of operations. And we just write the sequence of those operations. We'll see examples of other computations later in this talk. Okay, two other things. We have in Haskell exceptions, runtime exceptions. This mechanism is similar to other programming languages, in fact, like in Java or C# or many other programming languages. We can throw exceptions everywhere in a program, like we can throw exceptions in pure code, in IO code, no problem. one limitation is that we can catch them only in IO code. And exceptions are not only for exceptional situations, like to show errors. For concurrent programming, as we'll see, it's also a tool for communicating between threads. So what is exception? It's just one way to send a message from one thread to another. Okay, so we'll see this idea later. But we have exceptions in Haskell, and otherwise it's just almost the same as in other programming languages. And another thing, just to finish this Haskell overview, is another idea. Haskell program is executed by runtime system. Whenever you write main function in Haskell, it's not your main function. It's actually a runtime system which executes your main function. So Haskell program is compiled, and then we have runtime system, which is implemented in C, and it's another part of our program. And this runtime system is responsible for many things, including memory management, like garbage collection. It is responsible for input-output, for concurrency, and for many other things. So we have this addition to our program. And this addition, this runtime system, is actually very clever. And it is doing many things in a very sophisticated way. And this runtime system is responsible for good concurrency implementation in Haskell. And I should say that it is really good. It is better, from my point of view, than many other concurrency implementations in many other programming languages. All right, that's it with my Haskell overview. And now we are going further. So we have two problems in concurrent programming, no matter the programming language we use. We have to run threads somehow, and then we have to synchronize them. We have to organize communication between those threads. And we'll talk about Haskell concurrency in these two parts. I'll start with running threads, how we run threads with Haskell, and then how we organize communication between threads. So considering running threads, one general point about implementation. In this talk, I will not go deeply into implementing multi-threading. But here we have a very basic principle that we have to understand before we talk about concurrent programming in Haskell. So suppose we have a Haskell program. Every program nowadays can, in every programming language, can use several processor cores, central processor unit cores, and it can use operating system threads. But the problem with operating system threads is that they are very heavy, because operating system has to keep a lot of information about those threads. Like creating those operating system threads is a very expensive operation. It takes a lot of time, like, well, if not seconds, but milliseconds, that's for sure. And that's quite a big time only to create thread. So what we usually have in Haskell, we have several operating system threads which can execute a lot, like really a lot, like thousands threads implemented at the library level. So concurrency library is part of the standard library of Haskell. And this library allows us to run millions of threads. And those library threads, they're very lightweight. So it just takes very little time to create them. They are very cheap. We can kill them, we can run them again. So it's cheap operation, and it's okay to do that. It's okay to run thousands of library threads. So this number of library threads, say n, is significantly greater than a number of operating system threads. And traditionally, we use several, like 5 or 6 operating system threads, and then we use thousands of lightweight library threads. So using this mechanism, the library implements preemptive multitasking. It's like if you have only one core, if you have only one operating system thread, it's not a problem. You can run thousands of library threads anyway using preemptive multitasking. You just stop running one thread and then give a chance to other thread to do something. So this is basic idea of implementation. And the main goal of why I am telling this to you, because one principle, which is very important for Haskell programming, we are free to create threads whenever we want to. It's a very cheap operation. And it's okay to structure our program as 1,000 of threads which communicate with each other, but which solve one problem. Okay, so this is several words about implementation. And now we are ready to discuss basic concurrency operations. So in Haskell, in standard library, we have this data structure, thread ID. This data structure encapsulates some information, not very much information about our thread. To run a thread, we use function fork IO. And what is a thread in Haskell? It's just IO action, and fork IO function is responsible for running this IO action in a newly created thread. So you can see here, IO unit, this is a type unit, which means it has only one value unit. So just to say that, well, there is some value, but it is not important at all. So this is IO action, and we give it as an argument to the fork IO function. And as a result, this thread is created, its executions started, and we have thread ID as a result. So we can operate with this thread ID somehow. So here we just create thread with this IO action as a body of that thread. So, and in fact, this is everything that we need to run a thread. We have some other functions, very specific. Sometimes we would like to run our thread in a very specific operating system thread. Such threads are called bound. They're bound to some specific operating system threads. But these are rarely used features. So this fork IO function is the main working horse of running threads in Haskell. We can also send an exception. I told you that this exception mechanism in Haskell can be used to communicate between threads. So this is an idea how we can communicate in this way. We just send an exception to that thread with some information E. For example, we can kill that thread if we know thread ID. We can kill that by sending specific sort of exception, like kill them all, something like that. We can use this to organize several threads which work in some system if we want that. But the main idea is to use fork IO, and that's enough. Okay? Just one simple example of how we can do that. This is a complete example of a program in Haskell. We have two IO actions. The first one prints string hello here, and another one prints string world. So I would like to get hello world printed in standard output. I run those actions using fork IO here, and then I receive their thread ID. And then just to see how things are going on, I print these thread IDs here. So I print the first one, print the second one. And as usual with concurrency, the result of executing such program is a little bit unpredictable. For example, I've run it twice on my machine, and this is what I've got as a result. So you see that there is now this phrase "hello world" here. But what we have like 3 in the beginning, and then we have age, the first symbol here, and then we have world, the first symbol from the second action. And for example, these are just fragment of hello, or maybe it's not hello, maybe it's one L is from one function, another L is from another action. So we have only one resource, like standard output, and these two actions compete for access to that resource. And we can also see that this print works first. So it takes some time to create thread, to start executing that thread. So, but this second print is just afterwards. So we were able to print everything here and here before going to the second print thread 2. So this is concurrency. If we want to control what we are printing, then we have to synchronize. But we'll talk about that later in this talk. So this is concurrency. This is the simplest possible concurrency program in Haskell. You see that it's really very simple. We just have a main function with 2 IO actions and 2 fork IO calls. That's it. So nothing special. In fact, I think no one in Haskell using fork IO nowadays, because we have much better interface for running threads. We use the Async library, a library for asynchronous computations, because it's much more convenient. It's much easier to write meaningful programs using this library. So it's a de facto standard for implementing concurrent programs in Haskell. So whenever you program in Haskell, you have to master this library. So in that library, we have an idea of asynchronous computation. It is encapsulated in this type, async A. This is an asynchronous computation, which eventually results in a value of type A. In other programming languages, we use words like promise or future. So why future? Why promise? Because it's a promise to return something of type A once the computation is over. So of course, when we run such a synchronous computation, the library creates a thread and run some IO action there. So, but then we get a result after this computation is over, once the computation is over. And we have several simple functions to work with those promises. So we have a function async to run IO computation. So here we have IO computation which results in A. And as a result of running this function, we get asynchronous computation. Once we have this asynchronous computation, we can wait once it's ready, once everything is computed. We can do that using wait function. So it just waits. It blocks the thread we are running this function until the result is ready. We can cancel this computation if we don't want to get that result. That's okay. And we can also poll this asynchronous computation, like meaning we can ask questions. So is this computation over already or not? like as a result, we can get this type maybe here. Maybe means either something or nothing. So if as a result of poll we get nothing, that means that, well, it's not over yet. We don't have result yet. If we get something, and something is either exception or value of type A, this means that as a result of computation, we can get some exception. For example, if this synchronous computation failed somehow, or it was killed by someone, in that case, we will get this exception. Or eventually, we can get a value, result of that computation. And this is usual idea when we are doing concurrent computation. We can either block if we have nothing better to do, or we can poll and ask if it's ready. And if it's not, then we can do something different. So very basic mechanism. Well, you may think that there is a lot of other functions in this interface. Well, in fact, there are some functions, but we can do everything with only this simple interface. But for convenience, we have something else. So this is another simple example. So just imagine that get URL function just download some resource from web. And in this example, we just run 2 asynchronous computations. We allow to execute these downloading processes concurrently in parallel. And then we just wait for the first result and then for the second result. So you can see here blocking. Wait is blocked call. So wait waits until the result is over. And here we have some ordering. So we wait for the first result, and then we start waiting for the second result. Chances are that second page is downloaded quicker. But anyway, we won't get to that until we get the result of the first one. So if we don't want that, so for example, we would like to get some result as quickly as possible. If it's the first one or second one, doesn't matter. And for such cases, we have another waiting functions in this async library. For example, we can wait for any result. So function wait any takes a list of asynchronous computations and returns the first one which was successful. So here, as a result, we can get the type for that computation and its result. And in this case, we just ignore every other computation. We just get the first one which has finished. This is the function over list. We can wait for 2 computations, 2 asynchronous computations using wait either. This function waits for the first of these 2 given computations and gives it back. And then we can also wait for both, like 2 waits in order. It's just the same as waiting both computations to be completed. So we can use these functions and we can implement the exact idea. What do we actually want in our algorithm? This async library allows us to write programs without thinking about asynchronous computations at all. For example, this set of functions mention no asynchronous computations. We can run arrays between 2 IO actions, like IOA and IOB. Race meaning run these 2 computations concurrently and gives us a result of that computation which was completed in the first by the first way. So the first one will be returned here in this type. Either A or B means it's either first result or the second result. We have a function concurrently, which runs 2 actions, IO actions concurrently, as we can see, and gives us both results. So it will be it will wait for those both results ready. We can go over a list of functions and run all of them concurrently, like here, map concurrently. This traversable is another example of type class for containers. We just go over every element of container and run some concurrent computation, some function over it. So every element of the list will be processed concurrently at the same time, if we have enough cores in our central processor unit. And another function, replicate concurrently, which allows us to run the same action specified number of times. And everything will be concurrent. So you see here that this high-level interface is very convenient, and we don't have to think about concurrency. We just write our actions like in usual Haskell, traditional Haskell, but then we write them concurrently without thinking about concurrency at all. Using these functions, we can rewrite our simple example for downloading something from internet as follows. We just run concurrently and those two actions for downloading element. So this is a good thing about high-level interface. Whenever you have a good high-level interface in any programming language, you don't have to think. You know, for programmers, this is a good feature of a programming language. When you are required to think carefully, then, well, we don't want to think, and if we think, we can do something mistakenly. And whenever we don't have to think, well, there is no place to make a mistake. So this is a good thing. So using this high-level interface, we can achieve very safe, very correct program. So this is our goal, to write good programs which are safe to use. So this is what we are thinking about in Haskell every time when we implement such mechanisms for doing something using this programming language. These are my key points for this first part about running threads. Of course, we have lightweight threads which are implemented in the library level. They are very cheap and we can run them as much as we like. Like we can run thousands of library threads, and that's okay. We have low-level interface, which is not used directly, but of course it is used in the implementation of the async library. So this fork IO function, it is defined in the control concurrent module of the base package, the main package for the standard library of Haskell. And we also have high-level interface, which is something which is always used whenever you write a program in Haskell, whenever you want to run it concurrently, the async library. This library, it has special status because it was implemented by the same person who implemented the low-level interface, Simon Marlowe. He's the author of the async library and the low-level interface for concurrency in Haskell. So he knows everything about that intimately. He also implemented the part of runtime system, which manages concurrent programming in Haskell. So he knows exactly what should be done in Haskell concurrently. So he implemented all this stuff, and well, now we just use them just as the main way to write concurrent programs in Haskell. All right. By the way, do we have some questions now before I'm going to the second part?
We had a question about what is either, but then it was answered by
okay, great.
co-host.
Yeah, so I'm sorry, it's very difficult to talk about such things as concurrency just after short overview of Haskell. Of course, well, we have to understand a lot of things about Haskell. before getting to that. Like in my book, it's chapter number 16. And I think that it's important to read everything else before that. Of course, as usually authors, they like when you read books from the very beginning to the very end. All right. Synchronizing and communicating is something which is usually considered very difficult problem in every programming language. Running threads is easy. Just absolutely, it's an easy problem, even with low-level interface. But synchronizing those threads, organizing, communicating between them is really hard problem. And as we'll see, in Haskell, it's not a problem. It's actually easy thing. So you may heard about many concurrency or synchronization primitives that are used in operating systems and other programming languages. Like you may heard about synchronized methods and monitors in Java, and just condition variables, some barriers, critical sections, and semaphores maybe. Like in concurrency courses, they always like to talk about semaphores, mutex, mutual exclusion, and things like that. Well, the good news is that we don't use all this stuff in Haskell. Well, we have semaphores, but technically we don't have to use them. And in Haskell, we work in a very different way. We never think about mutual exclusion or spin locks or reader-writer locks. The only mechanism that we have in Haskell is that we synchronize on data access. We have types which are implemented in a way that data access to those values is exactly synchronizing. So we have blocks, we have waiting on those data values of very specific types. So no mutexes, just data access to some special variables. In Haskell, everything starts with so-called mvars. We say mvars. It's synchronizing mutable variables, but everyone calls them mvars. So it's some data type. It's a value of type A, which is either empty or full. And here you can see some drawing. Like we have empty variable and we have full variable with a value inside it. We can we have an interface for creating these mutable variables. Two functions. We can create them empty, we can create them full. So here we create mvar of type A as an empty mutable variable, and here we create it with a value of type A. So we have two ways: create empty, create full. But when do we have synchronization? Well, it's about other functions which allows us to take those values. So we also have take mvar function, which blocks if the variable is empty and returns us a value if there is a value in that variable. And whenever we take that variable, we just make this box empty. Like if it is empty when we call take mvar, then we block, our thread blocks and waits until it is not empty. Once it is full, so not empty, we take that value out of it. And now you can see this synchronization. If one thread put value to this box and another thread take value from that box, then we synchronize these two threads on this value. So it's synchronization and it's also communication, because one thread puts value, another thread takes value. So we have synchronization and communication on the same variable here. And we also have put mvar function. This function just put a value into this box. If it is full at the time when we run this function, then we block. So it's impossible to put some value into a full mutable variable. Once it is empty, we put that value, and then now it fulls. When we exit put mvar function, the box is full with the value we've just put into it. So these two functions for taking value and putting value, they're main basic blocks for any synchronization, any communication in Haskell. There are other functions as well. For example, we can read mvar. Read mvar doesn't change the value. We can just look what is inside it. If it's empty, then we block. If it's not empty, we just get a value, but we don't remove it from that box. And of course, we also have non-blocking operations like this try, take mvar, try, put mvar. These functions, they just attempt to do something, but they can give us an information if they fail. Like for example, try, take mvar will give us nothing if it is empty. And they are non-blocking. So if it's empty, we can see that from the result. Try, put mvar gives us either true or false. And if it's full, we get false, and it means that this operation was unsuccessful. And we can also check if the mvar is empty using this function. But of course, whenever we think about concurrent programming, we should always understand that functions like that, they are something that is not very reliable. If this mvar is empty at the moment when we run this function, that doesn't mean that it will be empty in a second or in a millisecond. Chances are that right after calling this function, someone just put a value into that mutable variable. So while doing concurrent programming, we almost never use such checks. They're useless because, well, it will be not empty in a second. So we cannot rely on it. Unfortunately, if you want to work with mvars, then there are very good chances that you do some error. Why is that? Well, mvar is a synchronization primitive, which is very difficult to get right. So I will show you an example, which is, well, not very realistic, but which shows that it's very easy to do something mistakenly. So here, suppose we have a main thread where we created two mutable variables here with two values, 1 and 2. And then we also have threads, two threads. These threads, they are very similar to each other. There is only one difference. Here we look at first at the first variable, then at the second. And here we look at the second and then at the first one. If we run these threads in order, like this, first we run the first thread, and then we run the second thread, then everything works as a charm. But if we imagine different order of execution, for example, if we try to take first variable here, and we have value there, so we're successful. And right after that, we run the first line here. So we take something from the second variable. Then we have a problem. Why? Because here we want to take second value, but there is nothing at this moment, and we block at this call. But the second thread is also blocked because there is nothing in the first variable. And what we have here in this example we have a potential deadlock that no thread can go from this point. So when we run this program, we can get a deadlock. It's potential. It is potential. We can just go smoothly if these two operations are not divided by execution order. But if we run first line and first line here, second line here, second line here, then we have this deadlock. And of course, we cannot guarantee this order of execution. Of course, programmers who are doing concurrent programming, they know that there are many ways to avoid such problems. So, for example, one general rule is that you should access these variables in the same order all the time. So you are not allowed to switch order, like first, then second, in every thread. This guarantees in this simple example that you'll get no problems. But unfortunately, this is difficult. Once our programs become a little bit more complex, it's not so easy such problems there. In this simple problem, even runtime system is able to see that we have a deadlock, and it will break our program with an exception, and it will say, well, this is a deadlock situation. But there are cases when it's not possible, and it's very easy to do this mistake. So MVARs, they are good low-level mechanism, but just as with low-level thread system, no one uses it, or at least mostly programmers try to avoid this mechanism because it's very difficult to do everything right. But still, it's a brick, low-level brick, which helps us to build everything else on top of this mechanism. For example, in the standard library, we have channels. This is a mechanism which extends mutable variables. It's like mutable variables with many values. So we have a channel, it's like a queue. It has first in, first out access. So it is some data structure, like here. We put values on one side of this channel, and then we receive them, we get the values from other side. And we are guaranteed that we take one element every time, and we take it only once, and we can put element only once. And if the channel is empty, then we are blocked on that. So we use this for synchronizing and for communicating between threads also. So just one thread sends elements to this channel, and another thread can read elements from this channel. And we have this type for that, chan A. It's a channel with elements of type A. We also have several functions for creating channel, for writing to this channel, and for reading that channel. Writing channel is non-blocking, reading channel is blocking. So this is an idea of an unbounded channel. We can write elements to the channel without any limitations, but we can read them only if there is something in that channel. Otherwise, we block. And these channels, they are quite sophisticated things. For example, there is a function for duplicating channel. And duplicating means that we have several channels, and we can receive one element several times. Like if someone writes this channel from one side, then we can receive it in duplicating channels. So this is an example of broadcasting. So we send it once, but then we receive it in many copies. This is also possible with channels. Sometimes we need this broadcasting. Sometimes we don't need it. Sometimes we want, like, every element goes to this channel once and is received also only once. This is what we usually expect from the channel. This is not just a data structure, not a synchronizing data structure. It's also a way to organize our programs. So how we can use channels in Haskell. For example, we can implement traditional concurrent master workers architecture with them. We have some master. This master creates tasks for threads, and these tasks are sent to the channel. And then we have several workers, other threads, and every worker takes an element, a task from the channel. And you see here, I'm using lines of different kinds. So I have dashed lines, and I have solid lines here. So every element is received only once by one of the workers. So for example, in this picture, some element was received by, some task was received by this worker, worker number 2. But other tasks can be received by this one or that one. So everyone is read from that channel only once. And the idea is that master always prepares those tasks, and workers just implement, just fulfill or execute those tasks. So that's a very simple architecture, but it's surprisingly often used in many programming languages, not exactly Haskell, but in Haskell, it's one of the main ideas for organizing concurrent programs. Main thread which generate tasks, and many threads which execute those tasks, and they read them from the channel. If we get back to the code, we will see something like that. In master thread, we create new channel, and then using for_m function is just like a for loop in other programming languages. I just go through the list of tasks and write every task to the channel. This is what is written here in this line. For_m tasks write channel. It's like a for loop which writes every task to the channel. And in between creating channel and writing to the channel, we create all the workers, and they are waiting. Like at this moment, channel is empty. We give this channel to all the workers, but they are waiting. They are blocked on read channel. And once we started writing tasks to that channel, those master threads have to read values and execute those tasks. So they are doing something like that. So this is a workers loop. So we have worker, there is a loop inside it, and the body of this loop is reading task and executing it. So here I have only 3 functions, and that's enough for implementing such architecture. I have a function for creating channel, for writing to the channel, and for reading channel, which is blocking call, and this call will wait once we have a task available in this channel. So very nice feature of Haskell. Everything is organized around data structure. And it's very easy to work with it. And it's very easy to organize application around this data structure using just 3 function calls: new channel, write channel, and read channel. That's it. I should say, unfortunately, again, these channels, they are implemented via mvars. And unfortunately, it's very difficult to implement something else using mvars. Like sometimes we need different kinds of channels. But if we try to implement channels of our own kind, then we immediately see that it's almost impossible to do right. So it's very difficult. And there are also problems with performance characteristics. And mvars using locks very often. And you may hear that when we are doing many locks in our programs, when we have degraded performance, we may potentially have degraded performance because all our threads, they're just waiting on those locks. So it's not a good idea to use vars and channels which are implemented using those vars. The good news is that in Haskell we have something very different. And please remember two things from the very beginning, from Haskell overview in the beginning of this talk. In Haskell, we have IO monad. We have this way of sequencing operations and way of limiting a set of available operations. Like in IO, we can do everything, but we can limit differently. I've told you about that. So let's look at the mechanism which is implemented in Haskell about 15 years ago. And now this instrument, which is a mechanism which is called software transactional memory, is used in Haskell very often. There are implementations of this mechanism in other programming languages as well, but as far as I know, they are nowhere such powerful and such successful like in Haskell. And I believe that the success of software transactional memory in Haskell is because of this monad mechanism, this general mechanism for defining sequenced computations and limiting lists of available operations. So let's talk about this mechanism and see how it can help us. These are basic ideas of this mechanism. We have so-called transactional variables. I've told you that everything in Haskell concurrency is about accessing variables. Here we have this special sort of variables, which we call transactional. Why transactional? Because we access them in so-called atomic blocks, which we call transactions. The term transaction here is derived from databases. In databases, we have have several properties for transactions like atomicity, isolation, and several others. So here, our threads, those threads which want to access some transactional variables, their parts are organized in atomic blocks. And the idea is that these blocks, they are executed concurrently, and runtime looks for conflicts in that concurrent execution. And what is a conflict when we say about concurrent, when we talk about concurrent programming? Conflict is when we read some variable and at the same time concurrently try to write into that variable. This is a conflict because we can do reading first, writing second. We can do writing first, reading second. And depending on this order, we can get absolutely different results. So this is what we usually want to avoid in concurrent programming. We need some guarantees that something like that will never happen. So these are conflicts. If we read variables from different threads, this is not a conflict. We can read as much as we can. There are no limitations for reading. So we have these atomic blocks which work with transactional variables, and runtime system just log every operation, write somewhere in some journal, some log every operation with those transactional variables. Reading or writing or reading or writing, whatever. And whenever this runtime system see the conflict in those concurrent operations, concurrent access to these variables, it just blocks threads and tries to retry transactions started from the very beginning. So if there are conflicts, then every transaction is retried. And then we try to run it again until it successfully completed. We try to make these transactions short. This is a good idea to make them short. Just, well, if something is executed quickly, then we just make chances for conflicts much less. So we want that. But why all this works in Haskell? Well, because we have this STM monad in Haskell, just like IO monad, which allows us to access to transactional variables. And whenever we write this STM computation, we just use mechanisms in the implementation of STM to look for conflicts, to retry transactions, and to do everything that is necessary to do to guarantee the properties of those transactions. So thanks to monad mechanism, we have this control just built into Haskell programming language. We have IO monad, all right, but we also have this STM monad where we're not allowed to do input-output in STM monad, not allowed, because, well, if we do input-output, then we cannot retry. It's impossible. If we've deleted some file, then we cannot retry this transaction. It is already deleted. But if STM control access to only transactional variables, then we can, of course, change their values, just reverse them, make them look as if there were no operations over them. And this is how they implement this in Haskell. So these are basic ideas. And of course, it should be difficult to understand these ideas after this short explanation. In the end, I will give you a link to the beautiful explanation of STM and Haskell. So you will have to, and it's written without the requirement to know Haskell in advance. So I will give you a link. It's very good paper on that. So we have these variables, we have atomic blocks, and then we have a runtime which is responsible for looking for conflicts and retrying transactions. All this stuff, from the point of view of programmer, is about several calls. We have a function atomically, which executes STM computation as an IO action. So it takes STM computation and it runs this atomically, like in atomic block, like as a transaction. We also have functions for working with transactional variables. And see, look, here we have new, creating variable, reading and writing. We don't have take and put as in mvars, because we are not blocking in this call. So if there is no value, then there is no such idea of don't have a value, that there is no value. Transactional variables, they always have a value. So it's not just possibly absent value. They always have a value. We can write them, we can read them, just as usual variables. But access to those variables is controlled by STM monad. We can see it here, here, and here. The type of the result is always STM. And that means that everything is controlled by runtime implementation of software transactional memory. And we also have a couple of functions for manual management of those transactions. I've told you that the transaction is restarted, is retried when there is a conflict. But we can initiate this restarting using manually using this call to retry. If we look at the variables and see that there is a problem and that we cannot continue at this time, then we say retry. And then our code, our thread is blocked until something changes, something which could allow us to continue execution. And another primitive transaction management operation is or else. It takes two arguments, two STM computations, and it first runs the second one, And if it failed, if it was unsuccessful, if it retried, then it runs another one. So we attempt to run one computation, and if it fails, then we run second one. And this is basic operation for doing such things like how we can get the first completed result. Well, we write first one. If it failed, we run second one, and then we can add another one, third one, and so on and so forth. And then we just can see which one was completed the first or whatever. So this is basic instrument, but using retry and or else, we can implement anything we would like to implement in concurrent communication. I have only one simple example, classical example of demonstrating concurrent programming in Haskell with software transactional memory. It's transferring money between bank accounts. Let's suppose that we want to transfer some amount of money between two bank accounts. We have from bank account and to bank account. From and to, they are transactional variables. Here you can see their types. They are both tvars, transactional variables. And the task is to take this amount of money, to withdraw it from account and to put it to account. And of course, we need guarantee that we have sufficient amount of money. We have to guarantee that if we take it from one account, then it will be put to another account eventually. Like this money shouldn't be somewhere at the bank. If we take it from one account, it should end up in another account. So this is money. How we can do that using STM? Yes, and we look that this is STM computation. It's not IO action. So we are not allowed to do IO here. The only thing that we are allowed to do is to access transactional variables. That's it. Okay. So we read first account. Current from is the value amount of money at the from account. And now we have a choice. What if we don't have enough money to transfer? So if this current amount of money is less than the amount that we have to transfer, then we call retry here. And this means that, well, we have to wait until we have enough amount of money. How STM runtime knows that we have to block? Well, if we run this function atomically, then runtime see that we access to the variable from, and that's it. And right after accessing it, we decided that it's not time to continue this transaction. So this thread will be blocked, and it will be unblocked when the value of that variable is changed. When some other thread will change, like for example, we can get money from someone else to this account, the value will change, and then we retry this transaction, and then we run it through this conditional instruction. So this retry is blocking, and at the same time waiting when this variable will be changed, and waiting when we will be able to continue through this conditional operation. And we also have else part here, and else part is very simple. We are writing new amount to from account. We are writing new amount to the to account. And again, we are still inside the transaction, inside the atomic block. If we are executing this, and at the same time, we will get a request to the same variable from some other thread, then this transaction will be retried by the runtime system. So it will be retried automatically. And then it will be restarted in some random amount of time. So this is what we'll get finally with that. So very simple example, but here we have automatic retrying from the runtime system. Here we have manual retrying. Here we access several transactional variables. And this is a good starting point for understanding why do we need all this stuff. And it's very easy. There is no way to get, in this example, to get something like deadlock. So everything will be controlled by the implementation of software transactional memory.
Vitaly, we have a question about retry. So how does retry know what to retry if it doesn't take any arguments?
Very good point. Because this retry, it's a signal to the runtime system. And runtime system knows that we are inside a transaction, inside an atomic block. And this runtime system keeps a log of all operations inside this transaction, this particular transaction. So runtime system knows that we've accessed from variable. So we just, this is a signal to runtime system. Well, look, we cannot continue. Just analyze variables we were accessed before in this transaction. And that's why it knows everything. So it's just a signal. And runtime system knows everything. It keeps the log of operations that we are doing inside the transaction, gives the list of transactions that are executed at this moment. It knows everything about that. So we're just signaling to it. We just say, well, look carefully. We have a problem in this particular transaction. Hopefully this answers this question. Yes. So we don't need to give another information. The runtime system knows everything about this transaction and all other transactions which run concurrently. So programming with STM is a very nice programming. And that's why we've got a lot of data structures, very sophisticated data structures, which are implemented on top of STM transactional variables. Some of them are implemented in the main implementation, in the main package STM. Some other are implemented in external packages like STM chants, STM containers. But these implementations, they are very good. And let's see what do we have among the data structures implemented on top of tvars. We have so-called tmvar, which is a reminiscent of mutable variable which can be either empty or full with take and put. And this variable is implemented using transactional variables, and it's much more safe to use in comparison with traditional mutable variables, mvars from base. So we can, and it's very easy to implement tmvars using tvars. It's just simple exercise. We also have channels, transactional channels, channels with an ability to duplicate, to do broadcasting. They are implemented using STM channels, tvars. And we also have queues. Queues are faster in terms of performance than channels, but they don't allow duplication. So queues just, again, first in, first out access, and we just write from one side and receive from another side. It's a very good way to implement master worker architecture instead of channels. If we don't need duplication, then it's a good idea to use queues instead of channels. But we also have bounded channels and queues. And bounded means that we have a size, we have a limit of size, like 1,000 elements. And after filling all the 1,000 elements, every attempt to write to the channel will be blocked. Usual channels, they are unbounded, so we can write and write and write, and this could lead eventually to some memory problems, not enough memory errors. We can get that if there is not enough memory. But with bounded queue, if we have a very powerful producer of data, then it will be just blocked, and that's it. So this bounded channels and bounded queues, they are good for performance and memory usage. So this is a choice which you have to, so if you don't need duplication, then you just go with TBQ and that's it. So this is the best idea, to start with this data structure and then see if you need something else. We also have closable channels and queues. Closables means that we can say that we've closed this channel. So we just say, well, there will be no values from this point. It's like closing the file. And if you receive, you can either receive value or you can receive an information that there will be nothing. So you can just stop operating. So this idea is also can be implemented in a very simple way using transactional variables. And we also have bounded closable channels, very sophisticated. But if you look at the implementation, you will see that it's not very difficult to implement things like that using transactional variables. And we also have containers such as set and map, dictionaries, associated lists. These are implemented using STM, and they are non-blockable. They are very good for concurrent access. They work very well in terms of concurrency. We can access them for reading and writing, like concurrent hash map in Java, for example. They are very good for reading and writing, and we can use these containers for reading and writing too. So we have all this stuff in Haskell, and we can it is implemented using transactional variables, and all this stuff is production ready. So we just use them in industrial application, and everything works. Key points here. So we have data access as a main point for synchronization and communication. So we synchronize on data access, we communicate through data access, and we also organize our programs around this data access. So we just, this master workers architecture is just one example of organizing a program, concurrent program in Haskell. And we can do that using channels or queues or whatever. So this is what we have in Haskell. And to complete this lecture, I will give you several sources how you can learn all this stuff. So if you don't know Haskell, I recommend to start with the book Get Programming with Haskell, which is really very, very good. So I was a technical prover for this book, and it is written in a very good way. It's just for absolute beginners in Haskell, but it goes to quite a good level, quite deeply in Haskell. So it gives you a lot of information, and there are a lot of exercises there. You can just learn Haskell in a very good way, in a very good, let me say it, in a very good order. And it's quite modern Haskell. And after that, well, of course, you can read Haskell in depth, but now I would like to recommend another book by Simon Marlowe, the guy who implemented runtime system for concurrency, low-level interface for threads, and the Async library. Simon Marlowe, he wrote this book, Parallel and Concurrent Programming in Haskell. It is a beautiful book. So it's not about just person who knows this stuff, but he also he has great examples. And I believe that this book is very helpful even if you are doing concurrent programming in other programming languages. It just it gives you a framework to think about concurrent programming in general. And in this book, you can see how the Async library is implemented. It's also very useful reading. You just understand why the things are done in the way they are done. So I recommend this reading this book very much, even if you are not Haskell. It's a very good book, very well written. And the good news is that it is accessible for free from the side of the website of the publisher. You can just read chapter by chapter, no problem. No need to buy. Even if it is a little bit, well, it's not outdated. It's 7 years old, but it's not broken. You can use STM, you can use concurrency in Haskell just as you could use it in 2013. Everything works. There is no need to rewrite, to fix STM library, for example. There is no need because there are no errors there. Like for 7 years, no one just found an error. So it's a very good library and very good book. And also, I would like to recommend this paper. It's actually a chapter to the book Beautiful Code. And this chapter was written by Simon Peyton-Jones, one of the most important figures, people in Haskell community, one of the creators of Haskell. And this chapter is called Beautiful Concurrency, and it describes the implementation and ideas behind software transactional memory. There is a very, very interesting and funny example about Santa Claus. Santa Claus problem is solved using software transactional memory. It, despite the fact that it was uploaded in 2016, it's actually a paper from 2007. So it's also quite old, but it explains software transactional memory using very good examples. So I recommend reading this stuff. And well, I think that's over. So if you are interested, you can look at my YouTube channel. There are many lectures in English on Haskell and other stuff. So thank you very much. If there are any questions, I would be happy to answer them.
Thank you very much, Vitaly. Thank you very much. It was a great lecture. So we have several questions actually. The slide before the money transfer example.
Okay, let me open it. Here.
Yes, so the question was here, when is a conflict detected? At trying to commit a transaction or already at the read of a variable that has been written by some other thread?
Good point. Well, technically, in nowadays, in the current implementation of transaction, conflict is determined at the time of committing. But it's not part of a specification of STM. It's just part of implementation, current implementation. Whenever we try to commit, so in the exit of atomically call, at this point, the conflict is detected and either retried or not. Or if we are using retry, then it's well, if you do it manually, then it is retried at this very moment. But technically now, at the time of committing this transaction. And committing in Haskell is just exiting this atomically function. Mm-hmm.
Yep, thank you. Then the next question, so just before you introduced mvars,
mm-hmm.
So just before the second part started.
Somewhere here.
Maybe before that, the slide before that, there was maybe even before this, there was example of, yes, so So the question is, why the constraint foldable T on LM? Why not traversable T? It's probably not this slide, but
okay, maybe where do we have foldable? Foldable was in the very beginning, I think here. Well, every foldable is a traversable, and that means that foldable is more general requirement. So whenever you have a traversable, then you also have a foldable. If you have foldable, then it doesn't mean that you also have a traversable. So LM is possible to do for every foldable, including traversables. So that's the answer. So foldable is more general. We can apply it to more types than just traversable. So that's why here we have foldable, and then later we have a traversable. Traversable in this interface means that we need something else besides just folding some container. So that's the difference. Traversable is less general.
thank you. And then the other kind of general question, so is Chan an alternative to mvar for mutable variables?
Well, I wouldn't say that it's an alternative. It's extension. So it's something which is more powerful than mvar. Channels are implemented using several mvars. So we can think about it this way. mvar is a channel, is a bounded channel with only one element. And channel can contain many elements.
So if there are no more questions, then I would like to thank Vitaly very much for this wonderful lecture. And I would also like to thank all the participants.
Yeah. Thank you.
The lecture has been recorded and will be published